All right, let's dive into one of the absolute biggest questions we could possibly ask. How is this whole story, the story of our universe, finally going to end? We're about to take a journey to the very edge of time itself to see what the ultimate fate of, well, everything might be.
So, how will it all end? Is it going to be with a giant bang or just a quiet whisper? A spectacular collapse back in on itself or just this endless, lonely expansion into nothing? For most of human history, this was just pure guesswork. But today, cosmology is basically a detective story, and the clues, well, they're pointing us towards some seriously mind-bending conclusions.
And here it is. This is the central clue, the big twist that basically changed everything we thought we knew. Back in the late 1990s, astronomers made a shocking discovery. The expansion of the universe isn't slowing down because of gravity, which is what literally everyone expected. Nope, it's speeding up. Something is out there pushing the cosmos apart faster and faster. And to even begin to understand what that something is, we've got to look at our universe's very, very strange recipe. So, Section 1, our universe's dark recipe. And you're about to see that the main ingredients dictating our cosmic destiny are almost completely invisible and totally mysterious. This is what just blows my mind. Look at how little of the universe is, well, us. This chart shows that a whopping 95% of the entire cosmos is made of two things we can't see and we really don't understand: dark energy and dark matter. Okay, so let's start with the big one, dark energy. This stuff is the dominant force in the universe, making up about 68% of everything. The best way to think about it is like a kind of cosmic anti-gravity that's literally woven into the fabric of space itself. It has this bizarre property called negative pressure, which basically just means it pushes everything outward. It's the engine driving that cosmic acceleration we were just talking about. And then we have dark matter. This stuff is completely invisible. It doesn't shine, it doesn't reflect light, but it has gravity, a lot of it. It basically acts as the invisible scaffolding, the cosmic glue that gives galaxies and galaxy clusters the framework they need to form and to hold themselves together. Without it, we're pretty sure galaxies like our own just wouldn't even exist. Which leaves us with this tiny number, just 5%. That's it. That's all the normal matter. Everything made of protons and neutrons. Every star, every planet, every single person, every single thing you've ever known is crammed into this tiny little sliver of reality. It seems our cosmic fate is completely in the hands of the 95% we can't even see. So for our second section, we have a cosmic disagreement. See, this detective story of ours, it's got a problem, a big one. As scientists try to measure exactly how fast the universe is expanding right now, their clues just aren't adding up. There's this huge disagreement right at the heart of modern cosmology. It's called the Hubble Tension. And here's the deal. When we look at the very early universe and use our best models of physics to predict what the expansion rate should be today, we get one number. But when we go out and measure the expansion rate directly in the modern universe, we get a different, faster number. And they shouldn't be different. Let me show you the problem in numbers. The data from the early universe, that's the stuff on the left, it predicts an expansion rate of about 67 kilometers per second per megaparsec. That just means for every 3.26 million light years you go out, space is expanding 67 kilometers per second faster. But when we actually measure things today with telescopes, we get a faster number, closer to 73. And believe me, in cosmology, that is a huge difference. So what gives? Are the scientists on both sides just making some tiny measurement error that they can't find? Or, and this is the really exciting part, is this tension a crack in our understanding of the universe? Is it a sign that we actually need new physics, something beyond our standard model, to explain what's happening? The jury's definitely still out on that one. Okay, Section 3, 5 ways it could end. Now, all this uncertainty, especially around dark energy and the expansion rate, leads us directly to several possible endgames for the cosmos. So let's explore the finales, shall we? First off, let's just clear a couple of the old theories off the table. The Big Crunch, the idea that gravity would eventually win and pull everything back into one tiny point, that's now super unlikely. Why? Because we know the expansion is accelerating. Gravity is losing the tug-of-war, not winning. And that also means a cyclical big bounce model is probably out too. Then you've got the wild card, the Big Slurp. This theory is wild. It suggests our universe might be in a sort of unstable state, a false vacuum. If even a tiny patch of space somewhere collapsed into a more stable, true vacuum, a bubble of new physics would expand out at the speed of light, rewriting the laws of nature as it goes, and just obliterating everything in its path. No warning, just gone. Okay, so setting that terrifying thought aside, most scientists are focused on two main scenarios, and both of them depend entirely on how this mysterious dark energy behaves over time, and they could not be more different in how they play out. So first, we have the violent end, the Big Rip. This would happen if dark energy isn't constant, but is actually a type of phantom energy that gets stronger over time. If that's the case, the expansion would accelerate so violently that it would eventually overpower every other force in nature. It would literally tear everything apart in stages, just like you see here. First galaxy clusters, then galaxies themselves, then stars and planets, all the way down until even atoms and the fabric of space-time are ripped apart. The second main contender is a lot quieter, but honestly, maybe even more profound. It's called the Big Freeze, or the heat death. This is a story that unfolds on timescales that are just impossible to imagine. After 1 trillion years, the last stars will have burned out. The universe will go completely dark. Over hundreds of trillions of years, galaxies will dissolve as their dead stars are flung out into the void. And then, after a Google years or more, that's a 1 with 100 zeros, even the supermassive black holes will slowly evaporate away, leaving behind, well, nothing. Which brings us to our last section, the most likely finale. So we've got a violent rip on one hand and a cold, quiet fade to black on the other. Where does the actual evidence point today? What's the most probable ending to our cosmic story? Well, based on everything we currently know, our best theory, the standard model of cosmology, it assumes that dark energy is what's called a cosmological constant. All that really means is that its strength doesn't change. It doesn't get stronger or weaker over time. And if that basic assumption holds up, then there's really only one fate in the cards for us. And here it is. Here's the verdict. The most likely scenario for the end of our universe is the Big Freeze. Not a fiery, dramatic end, but a slow, gradual fade into absolute zero as the universe just keeps expanding forever. It's a pretty bleak thought, but at the same time, it's just completely awe-inspiring, right? A universe that just keeps on expanding forever, getting colder and darker and emptier with every passing eon, until all the light and all the heat is gone for good, leaving just a vast, silent, and incredibly cold emptiness. Of course, this is all based on what we know right now. That Hubble tension we talked about is a huge reminder that our model might be missing something big. The ultimate key to our destiny is locked away in the true nature of dark energy. Is it constant? Is it that phantom energy? Or is it something else we haven't even dreamed of yet? The final answer to how it all ends, well, that's still out there, waiting for us to find it.